Welcome to Obhi's Math e-Pathshala. Today's topic is finitely generated abelian group.
So we have proved that where G be a non-zero abelian group, then the following are equivalent. That is, each non-zero element x can be uniquely expressed in the form x is n1x1 plus n2x2 plus nrxr for ni not equal to 0 for at least one I. And xi's are distinct elements of x. And number 2 is x generates G. And if n1x1 plus n2x2 plus nrxr equal to 0, if and only if n1 equals to n2 equals to nr equals to 0. So this 1 and 2 are equivalent to each other. So let us define. So these x, these generating sets having this special property, either 1 or 2. So this has important roles in finitely generated abelian groups. So let us define this set as, definition. So an abelian group G having a non-empty generating set X which satisfies one of the conditions stated in the above theorem is defined to be a free abelian group. And the generating set X is called a basis for the group. So an abelian group G having a non-empty generating set X which satisfies one of the conditions stated in the above theorem is defined to be a free abelian group, and the generating set X is called a basis for that group. So this set has a special role in abelian groups, or we will see that it has important roles in finitely generated abelian groups. Let us have a look at some examples that we have already encountered an example in our introductory session, that this group Z cross Z. So we have seen that this group is a torsion free group which is generated by the set 1 0 0 1. So actually this 1 0 0 1, this set has a special property that the way we have expressed a member of Z cross Z is unique. That is ij, these numbers are unique. For that reason, we can say that, so for example, Z cross Z is a free abelian group having a basis as 1001, having a basis 1001. In a similar way, you can have, in a similar way, a basis for the abelian group Z cross Z cross Z is the set 1 0 0 0 1 0 0 0 1, which says that this group is also a free abelian group. And generally speaking, Z cross Z cross Z up to some factor n is a free abelian group having a basis E1, E2, En, where Ek equal to 0 0 0 1 0 0 0 1 is at the kth place. Yes. So Z cross Z cross Z up to n factors is a free abelian group. Also, let us have a look at the group Zn. That is the finite cyclic group of order n. And we will observe that the group Zn is not free. Is not a free abelian group. For why it is not free? Because nx equal to 0 for every x belongs to Zn, although this n is not 0, which violates the condition 2 of the above theorem. And this says that you cannot find any basis in Zn. Now, let us consider let us consider a free abelian group. G having a finite basis which is x1, x2, xn say x, okay, xr say, yeah. So we have considered a free abelian group G with a finite basis x1, x2, xr. Now if x belongs to G be such that x is non-zero, then by the definition of a basis, then this x has a unique representation. Of the form x is n1 x1, n2 x2, nr xr for nk belongs to Z. Now due to this unique representation, you can set up a map phi colon G to Z cross Z cross Z up to R factors. So you can define a map phi colon G to Z cross Z cross Z up to R factors by the rule. So phi x goes to, so phi of n1 x1 plus n2 x2 plus nr xr. And with the help of this representation, you can define this function as, so phi of this is, it is n1, n2, nr. And of course, phi 0 will be 0. Now, let us check whether this phi is a homomorphism or not. Now for two elements xy belongs to G, we have phi of x plus y equals to phi of, now x can be written as n1 x1, n2 x2, nr xr plus, and y can be written as m1 y1, m2 y2, mr yr. This, okay. Now
স্যার এখানে y1 y2 yr টা তো x আরই হবে মনে হচ্ছে, x1 x2 করে।
কেন বলো?
এখানে তো x টা স্যার x1 x2 ডট ডট করে x আরই আছে, মানে ওটাই জেনারেট করছে।
Yes, 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 right. So x1, sorry, x1, x2, xr, yeah. So therefore phi equal to n1 plus m1 x1, n2 plus m2 x2, nr plus mr xr, yeah. So this proves that it will map to n1 plus m1, n2 plus m2, nr plus mr. Now again, it is the addition of nr plus m1, m2, mr. So this proves that it is phi x plus phi y. Right? So this is a homomorphism. So phi is a homomorphism from G into Z cross Z cross Z R factors. Now by definition, phi is onto. Phi phi is onto since any member n1, n2, nr belongs to Z cross Z will generate an element which is n1x1, n2x2, nrxr, which is in G. So this will generate an element. This belongs to G, which must map so thus we see that phi is a onto homomorphism. So therefore, by first isomorphism theorem, so G by kernel of phi is isomorphic to Z cross Z up to R factors. But now, if we calculate the kernel of phi, then we will see that this set contains all those x belongs to G such that phi x equals to the identity element of this group, that is 0, 0, 0 r times. Or you can write down that car phi will contain all those n1 x1, n2 x2 plus n3 x3 plus dot dot nr xr belongs to G such that n1, n2, nr equals to 0, 0, 0. So this implies that the only possibility is n1 is 0, n2 is 0, nr is 0. So the only possibility is it is a single 0. And hence G is isomorphic to G by 0, which is isomorphic to Z cross Z cross Z up to R factors. Okay, and thus we have proved that the theorem is that let G be a non-zero free abelian group with a basis of R elements then G must be isomorphic to Z cross Z up to R factors. Up to R factors. Thus, we have proved that if G be a non-zero free abelian group with a finite basis having R elements, then G will be isomorphic to Z cross Z up to R factors. Right? So this is a beautiful observation. Now, it may happen that a non-zero free abelian group may have more than one finite basis. If we consider a non-zero free abelian group with a finite basis, then there is a possibility that there may be more than one finite basis. Now the question is that every basis of G does they have same number of elements? Hello. The question is that do they have same number of elements? This is the question. The theorem says that yes.
Same number ही होगा.
Same number ही होगा. Yeah. That if we consider a non-zero, একদম. So if we consider
নিচের জন্য হচ্ছে
দেখো কি করে হচ্ছে দেখো
না ওই তো জি ক্রস জিটা হ্যাঁ এটার জন্যই হচ্ছে
এটার জন্যই হচ্ছে শুধু একটা ছোট্ট অবজারভেশন আছে প্রমাণটা let G be a non-zero free abelian group with a finite basis then every basis of G is finite and all bases have same number of elements. Yeah. So if G be a non-zero free abelian group with a finite basis, then every basis of G must be a finite set and all bases have same number of elements. So the proof is like that. Now let us consider a basis of G as, so let G have a basis, so let G has a basis say x1, x2, xr, say. Yeah. Then by using the above observation, we can say that G is isomorphic to Z cross Z cross Z up to R factors. Now, let us consider a subgroup which is denoted by 2G, whose elements are 2 into G, that is 2G means G plus G, twice, where G belongs to capital G. So which is a subgroup of capital G? Since why it is a subgroup? Why it is a subgroup? Since 2G1 minus 2G2, that is G1 plus G1 minus G2 plus G2. That means since the group is abelian, so we must have G1 minus G2 plus G1 minus G2. That is 2 G1 minus G2. So therefore it belongs to 2G. So 2G is a subgroup of G. Now since G is isomorphic to Z cross Z cross Z up to R factors, so we must have now since G is isomorphic to Z cross Z cross Z up to R factors, then what will happen? Then G quotient by 2G must be isomorphic to Z cross Z cross Z by 2Z cross 2Z cross 2Z, right? Since G is isomorphic to Z cross Z cross Z, then you can find out, you can define a map from 2G to this group, 2G to 2Z cross 2Z cross 2Z. And this map will be again an isomorphism from 2G onto 2Z cross 2Z cross 2Z up to R factors. Now what is Z cross Z cross Z quotient by 2Z cross 2Z cross 2Z? Now we may consider a map psi colon Z cross Z cross Z to Z2 cross Z2 cross Z2 up to R factors by psi of N1, N2, Nr goes to N1 plus N2 plus Nr plus. Now this map can be shown to be a homomorphism, since for N1, N2, Nr, M1, M2, Mr belongs to Z cross Z cross Z R factors, then psi of n1 into nr plus m1 m2 mr, which is psi of n1 plus m1 n2 plus m2 nr plus mr. That is n1 plus m1 class, n2 plus m2 class, nr plus mr class. So that means it is n1 class, n2 class, nr class plus m1 plus m2 plus mr class. So that is, it is psi of n1 n2 nr plus psi of m1 m2 mr. So this proves that psi is a homomorphism, and by definition psi is onto. So therefore, by first isomorphism theorem, so Z cross Z by kernel of psi is isomorphic to Z2 cross Z2 cross Z2. Now what is car psi? So now car psi equals to the set of all those n1, n2, nr belongs to Z cross Z up to R factor such that psi of n1, n2, nr equals to 0 plus 0 plus 0 plus. That means n1, n2, nr belongs to Z cross Z such that n1 plus n2 plus nr plus equals to 0 plus 0 plus 0 plus. That is, set of all those n1, n2, nr belongs to Z cross Z such that in k class equal to 0 class for all k equal to 1 to r. That means set of all those n1, n2, nr belongs to Z cross Z such that 2 divides nk for all k equal to 1 to r. So that means set of all those n1, n2, nr belongs to Z cross Z such that nks are of the form 2 qks for all k equal to 1 to r. So this means that, so these are all elements of the form 2q1, 2q2, 2qr such that q1, q2, qr belongs to Z. That is, it is 2z cross 2z cross 2z. So therefore Z cross Z up to R factors quotient by 2z cross 2z cross 2z up to R factor is isomorphic to Z2 cross Z2 cross Z2 up to R factors. So there, hence, so ultimately we have reached the isomorphism from G onto G by 2G onto Z2 cross Z2 cross Z2. So that is G by 2G is isomorphic to actually Z2 cross Z to R factors. And this implies the cardinality of this group must be the cardinality of this group Z2 cross Z2 cross Z2 R factors. That means it is 2 to the power R. And this implies R is log of 2 base cardinality of G by 2G. And this proves that which is a fixed quantity. Since G is the whole group and R equals to log 2 of mod log 2 of the cardinality G by 2G, so R is fixed here. So you cannot change R. So every basis has log 2 cardinality of G by 2G. So that means every basis is finite and has same number of elements for all the bases. So any two bases, so this proves that any two finite bases of G have the same number of elements. And lastly, so it remains to show that once a non-zero free abelian group has a finite basis, then that group G will not possess any infinite basis. Okay, and this way you can say that every basis of G must be finite. So it remains to show that G can't have an infinite basis also. Okay. For let us suppose that Y be any basis of G, and Y1, Y2, Ys be distinct elements in Y. So we have considered any basis of G, and also suppose that Y1, Y2, Ys be distinct elements taken from Y. And then we form the subgroup of G, then we form the subgroup H of G generated by Y1, Y2, Ys. That is, H is L angle, Y1, Y2, Ys R angle. And let us suppose K be the subgroup generated by the remaining elements of y. That is other than y1, y2, ys. So elements of y which are other than, which are different from y1, y2, ys. And this shows that, so every element of G, can be expressed as a sum of two elements. One element will be from H and the other one will be from K. Since G is generated by Y be a basis of G. Okay. So this shows that, and also H and K H intersection K is the singleton set identity. Here. So this shows that G is H plus K, H intersection K is singleton 0, that is the identity, and also H, K being subgroups of an abelian group are normal. So G is the internal direct product of H and K, and hence G is isomorphic to H cross K, which this implies that G quotient by 2G is again isomorphic to H cross K quotient by 2H cross 2K by the same arguments as we have already seen in this proof. We can say that G by 2G is isomorphic to H cross K by 2H cross 2K. That means it is also isomorphic to H by 2H cross K by 2K. Now cardinality of H by 2H is what is the cardinality of H by 2H? Since H is a subgroup generated by the basis y1, y2, ys. So in the previous arguments, we have seen that if G be a non-zero abelian group having a finite basis having R many elements, then cardinality of G by 2G is 2 to the power R. So in that case also, cardinality of H by 2H by the same arguments, we can say that it is 2 to the power S. It is 2 to the power S. And this implies cardinality of G by 2G, it must be greater or equal to 2 to the power S. that is 2 to the power r is greater or equal to 2 to the power s, and this implies s is less or equal to r. Okay, so this proves that y cannot be an infinite set for we would have s greater than r.
Thanks for watching. Please like, subscribe and share, and drop your comments in the comment box.